This lecture will introduce the convolutional operation. We will study about the discrete time version of convolution, and later we will study the continuous version. Before that, I would like to introduce RC circuit, because the RC circuit is a simplistic signal processing, and also it can be converted easily to the discrete version. And one of the important thing here is the convolution operation is a important characteristic of memory of A systems. So here RC has some single memory element I exist here. C works as a memory element. In the previous homeworks, we study about the RC circuit. We know that the terminal characteristic of a resistor through the Ohm's law and the capacitor store the charge. So capacitor terminal characteristics described by these differential equations. If we connecting this device in series patterns, the resistor current flow through the capacitor, so both of these current should be equal. So I would like to describe the behavior of the circuit. Here the current through the resistor are given by Vi minus Vo over R is the current based on the Ohm's law, or you can see here the resistor terminal voltage difference across the resistor. Vi is the for R plus, Vo is Vi minus, so the voltage difference across the R is Vi minus Vo. That's the current flow through the resistor. That current should be balanced with capacitor current. Capacitor case is C times dVo over dt. So both of Vi and Vo are time function. At this times the capacitor terminal voltage is Vo. Okay, so this system behavior can be rewritten like this way: dVo over dt equals to plus 1 over RC. Vo equal 1 over RC Vi. At here the RC should have a time dimension, so time unit. So RC means some sort of time. So I would like to replace the RC with tau. I mean RC, I will replace that one with tau notations. Then I can rewrite dVo over dt equals to Vi over tau minus Vo over tau. So in fact Vo and Vi are function of time, so I would like to this notation t, and this is t. Okay, this is this differential equation describe the behavior of RC system. It means that this RC system can be described like this way: input is at this moment is Vi t, and the output becomes Vot. The relationship between input to the output are given like that. So we would like to figure out the property of this system. To characterize this one, we need to apply some test signal at the input, and as a test signal, usually we are taking unit step or impulse are used. But in continuous domain, the impulse response is quite tricky, because it is infinite value at t equals 0, but the unit step is a little bit easier. So I would like to rewrite this one. If input is unit step, then we can figure out step response of the output. So I would like to figure out when input is applied as a unit step, then to find out the output response. We can safely assume that all the signals are 0 if t is less than 0. It means that if t is less than 0, so every event occurred after t is positive time. So if t equals 0, then VIT is 0 and VOT is 0. And in fact, we assume that the VIT equals to unit step. Unit step is this is 0 if t is less than 0, and 1 if t is greater than 0. So this one is a unit step functions. So we assume that the input is applied unit step, and before t equals 0, all the signal is 0. Okay. So these are the basic assumptions when we analyze the RC circuit. Then we would like to solve these differential equations. To describe that one, we can rely on the original equations. So dV O over dt plus V O over tau equals to unit step over tau, and we can add 0. This telling 0 gives a homogeneous solutions. It means that this equation can be decomposed into two different equations. One is that dVO of dt plus VO over tau equals to 0. You know that there is no signal source, so we call this response is sourceless response or homogeneous solution. And the other one, this one is OH, homogeneous solutions. Okay, and the another one is particular solution. We call that is the initialist response, dVOP over dt plus VOP over tau equals to 1. We think about this question at t is positive. T is positive. Okay, at t is positive, ut becomes the 1, so we can replace this one as a 1. Okay, like that. So we can decompose this one into two different equations, and our final solution will be plus, this is the general solution. Both VOH and VOP summing up, that is replace the VO into original equation, that will be satisfied the original equations. So we would like to figure out these two solutions. First, we will try to solve the homogeneous one first. So let's try this one. H over dt. This one is plus VOH over tau 0. We know that this solution should be a exponential function. We didn't know that this a coefficient, but that is the unknown coefficient, but we can figure out the a based on the initial value. The solution should be minus t over tau. It should be this kind of expression, or sometimes we can write down this is another. The exponent are expressed in this way, exponential function t over tau. Okay, this one are equals to these exponential notations. So VOH should satisfied with this equation. If you replace that one into here, then these equations will valid. Whatever A is, A, you can choose any kind of value. So any kind of any A value, this equation will satisfy. Okay, so we solve the homogeneous one first. Next one is particular solutions. Particular solution is very easy to solve by intuitions. So the VOP should satisfy these conditions. Okay, I can VOP, sorry, VOP T over tau should be 1 over tau. So we can try any particular solution that satisfies these conditions. So we can try as a constant 1. Okay, you can replace the VOPT is equals to 1 by taking derivative. It goes to the 0, but VOP is 1, so this equality is satisfied. So we got the solutions, homogeneous and particular one. Then we now write the solutions. VOT are given VOH T plus VO particular solution. This one says as a general solution for the differential equations. So we can now rewrite particular solution is 1 minus, and VOH are A C dot exponential minus T over tau. Okay, this is the solution, but we need to determine the A value. But we know that at the initial value at t equals 0 should be 0. Okay, from these assumptions we can figure out VO t equals 0 should be 0. Okay, this is our basic assumption. So based on that information, we can determine the A value. 1 minus A should be 0. Therefore, VOT are given particular solution minus T over tau. Okay, I can write down over here. So this is the solutions. Okay, so what did we do? At first, we build up the differential equations based on the terminal characteristic of resistor and capacitor. That's this one. And to solve the system behavior, we need to test this system with a unit step or impulse. But impulse is a little bit difficult, so we try to solve when we can test the system with the unit step functions. So we apply the unit step, but another assumption is this one, that initially all the values are 0. So at the t is less than 0, everything is clear out. So output is 0, input is also 0. So all the resetted conditions. At that conditions, we apply the unit step at the input. At the t equals 0, you mean that the t equals 0 is trigger time. So event occurred at the trigger. So this one is a specific times at the event occur. Event occur after t equals 0. So t is greater than 0, positive time. So we solve that t is positive conditions. In these conditions, we can rewrite the differential equation at here. The differential terms and v over tau. At this moment, the unit step is assumed that so at the t is positive time, unit step are equals to 1. So 1 over tau plus 0. So we can decompose the differential equation. One is the homogeneous one. That's this part. 0 equals to this left-hand side. And the particular one, left-hand side are equal 1 over tau. So we can decompose that one into, one is the homogeneous solution, the other one is a particular solution. So the actual solution should be sum of these two things. If you sum of these, this value, this output VO will satisfy these original differential equations. So we try to solve the homogeneous one first. Homogeneous solutions are easy to solve. This one is just a simple exponential functions. Differential equation always satisfied the exponential solutions, any a value. So V O H can be try a times e to the minus t of tau. By taking derivative with respective to time at these terms, minus 1 over tau will come out due to these exponential functions. So that will cancelled out at here. So this equality are satisfied whatever a is used. And the next one is particular solutions. Particular solution is this part. So, here one typo. It should be like that. Sorry. So this one are tested at here. If we try VOP as a 1, then the VOP plus VO over tau should be equal like that. You know that VOP is constant value 1. Time derivative should be 0. So VOP is 1, then this equality are satisfied. So we can figure out particular solutions. By adding the homogeneous and the particular solution, we can get actual solutions. Then you can write the solution like that. But A is not determined. We have to select the proper A value. To do that, we refer to the initial conditions of that. Initial condition of the system is 0. So we try to testing t equals 0, then this is 1. If we try t equals 0, then the exponential term goes to the unit. So it satisfies these conditions. So A is given. So we can finally find out the output response.